So, Stephen, was Rich's class really that? He just... All right, well, hopefully I won't do anything like that gross in here. All right. So we're into gases on chapter 14 and how the atmosphere has weight and mass. And let's put this over here for now. So that objects in the air displace air, and so they feel a buoyant force. There's density. If you're more dense than the air, like we are, we sink. But if you're less dense than air, like a helium balloon, you want to go up. And if you're hovering, like a blimp, neutrally buoyant. How does the buoyant force compare to the weight? Yeah, they're equal and opposite. So it's the same game there. I did mess up, though, which is why I was confused. At the very end of class, we did the straw, and I asked you, what's the theoretical maximum height a straw could be to still work? And I got confused because I was looking at the board, thinking the answer should be easy, and saw a number that I knew wasn't the right answer, and it was because I wrote the wrong number on the board. So let me correct that. Do it over here. Atmospheric pressure, 1 atmosphere, it's about 100,000 pascals. It is 760 millimeters of mercury. And then I wrote 29.92 inches, and I wrote water. That's not right. I should have caught it then, but I didn't. So that's of mercury. In other words, 30 inches is 760 millimeters. It's actually 405.5 inches of water. So if you had a tube connected like this, and if in one side you had water, what would the pressure be down here if this height was 405.5 inches? Yeah, that pressure. It'd be the weight of that water over that area, because that's pressure, will exert a pressure equal to 1 atmosphere right here. That's what you'd feel. How high would the mercury need to be to balance that? .29 inches. We'll round to 30. So let's see, not the scale here. That's 200, 150, about here. Mercury with a height of about 30 inches. Why is this so much smaller? This would be balanced. Do you believe me? If you had 30 inches of mercury over here, it would balance 406 inches of water over here. And they would come to an equilibrium. Meeting in the middle somewhere. Do you believe me? Good, thank you for nodding. I'm not trying to trick you. Why, though, is this one so much shorter? Not just because it's heavier, it's more dense. It's more dense. So it's heavier for the same volume of it. So because it's more dense, you don't need as much of it to have the same weight, force over that area, which is pressure. So the pressure here is the same as the pressure here. They're balanced, and you only need that much. That's a barometer. Oh, so this is the maximum theoretical height a straw could be. Because for a straw, you have your straw, and you're trying to suck up the fluid, right? You have to lower the pressure here compared to the pressure pushing down here, which is what? It's the atmosphere pushing on it. That's what pushes it. So if you, normally, this is the atmospheric pressure. And that's what happens. So if you make this lower, then this starts to go up because the atmosphere pushes it up because of this difference in pressure. What's the maximum difference you can attain? How low can you go? Yeah, you can get rid of all the air, right? So the pressure would be 0 up here. It's the lowest you can get. So what would the difference in pressure be? If it's 0 up here and an atmosphere down here? 1 atmosphere, or 100,000 pascals, all this stuff. And that's the same pressure that this amount of water would exert. So that difference in pressure, 1 atmosphere, could only lift up that much water. It couldn't lift up any more. So that's how high your straw would be. By the way, that's about 30 feet. So in case you can visualize it better. 10.3 meters technically. So yeah, you can get up there. And if you had a pump, like a vacuum pump, not just me going, and you could keep lowering the pressure lower and lower and lower until that got to 0. Then you really could. You could get water up theoretically 30 feet in the air by letting the atmosphere push it up. Now there are pumps that can increase the pressure down here. You could put the pump at the bottom. And if you increased this pressure, say to 5 atmospheres, by compressing the air, squishing it together, increasing the pressure, then you can, there's still that difference. You can just push it up. And then you can go even higher. But if you're just sucking, the atmosphere is doing the work, and there's only 1 atmosphere, so it can only go 30 feet up. So, next time you're trying to drink your soda can of pop on a stairwell, and I've tried it, you can't, it doesn't work beyond 30 feet. Does that make sense? It's just balancing the pressure there. So that's a barometer. Here's a makeshift one. It's just colored water. You can tell differences in pressure using one of these things. So the level of water in the bottle is the same as the level of water in the hose. Because why? This is loose. So it's atmospheric pressure here and atmospheric pressure here. They're equal. So they go to the same height. It doesn't matter that it comes down, whoa, or up, because the pressure's the same. It can even do the little loop-de-loo. But now, if I tighten this, it's still atmospheric pressure, but I'm going to start pumping on this side. This is one of those pump caps designed to keep your pop from going flat. Doesn't actually work, but there's a physical reason, but that's all right. So we increase the pressure inside the bottle, and there's a difference in pressure now between the 2 ends. How would we figure out exactly how much I increased the pressure inside the bottle? Yeah, the difference in heights. This is up here, this one's down here. If you measure that height, remember pressure is height dependent. What's the formula? I'd go write it on the board right now, but this will spill. Look in your notes or something. But pressure was based on the density of the fluid times gravity accelerating it down and the height or depth, however you want to look at it, this distance. So this column of water weighs something. It's acting over this area. So just from this column of water, from here to here, this is exerting a pressure right here. That pressure is balancing the increased pressure over here. They're exactly the same. And so you can use a barometer to tell what the pressure is outside. When a storm's coming through, usually the pressure drops. And so your barometer will move one way, and vice versa if the pressure increases. And that's how they measure. the difference. Does that make sense? Let's release this pressure and let the atmosphere go back to 1 atmosphere. And hopefully you saw it go back down. All right. Blow it in there. Less of it comes out into the hose, and I don't spill as bad. Where's my pressure gauge? How many of you used one of these? Probably most of you with your bicycle or a sporting ball or your car tires. So this measures the pressure inside your tire. There's technically a difference, though, between absolute pressure and gauge pressure. Gauges, pressure gauges, measure gauge pressure. That's the difference in pressure from inside to outside or one side to the other. So when you put this on there and it goes up to 32 psi, pounds per square inch, that's the difference inside and outside the tire. What would be the absolute pressure inside the tire, the total pressure? You have this pressure, but what else is pushing on it? The atmosphere. Very good. Let's draw a little picture. Or let's just go to this guy. Remember this height of water from here to here? That exerts pressure due to that column of water. And what was pressure? Density, gravity, height. That's how you'd figure that out. That's the pressure just from the water. What's pushing up here? The atmosphere is pushing on top of the water. So the absolute pressure right here, the total pressure, is that atmosphere pushing down on the top of the water plus the pressure due to the column of water. Does that make sense? That's what absolute pressure is. So the same thing's happening on your tire. The atmosphere is pushing in on your tire. But your tire has air shoved in it. And the pressure in your tire adds on top of that. And that's what you're measuring. So with your tire, absolute pressure of an atmosphere plus the pressure of your gauge. This is the difference in pressure from inside to outside. So that's all this measures. That 32 pounds per square inch is the difference inside and outside. You add that to the atmosphere that's still there pushing, and you get an absolute. Do you understand the difference between gauge and absolute pressure? Okay. So my point here, most of the time when people measure pressure, they're actually measuring a gauge pressure. It's just the difference from one side to another. Like this. That column of water is like this. And that's the difference from one side to the other. Air is still pushing. Go ahead. Oh, yeah, PSI. That one, I think I wrote last time, but it's in your book. An atmosphere is 14.7 pounds per square inch at sea level, room temperature. So to give you an idea, inside your tire, the pressure is more than 2 atmospheres inside your tire. The difference. Because it's about 30 or 40, depending on your tires. So it's about 2 atmospheres inside your tire. But if you add the atmosphere that's pushing on the outside, the absolute pressure then inside, like if you could physically shrink down, magic school bus and go inside your tire, you'd be feeling 3 atmospheres. Pop out of the tire, you only feel 1 atmosphere. The difference is 2, roughly. Glenn, you had a question? Yes. With the barometer there? So that example was kind of, we sealed this one off and the water level here was, say, here, and this one was up to here. So this height is that height. So if we do that, the difference in pressure from here to this surface to this surface, the difference there is the density of the water, gravity, and that difference in height. Or if it helps you, that difference in height. Yeah. So this is the difference. The pressure here is, D, G, H, just due to the water, right? That column. If you want the absolute here, you have to add on, well, this or this. You have to have that pressure due to the water plus the air that's still pushing down up there. So the absolute is atmosphere plus this difference. This is just measuring a gauge pressure, which is just that difference. Yeah, if you want absolute, you have to include the atmosphere. So here's the thing. If you go scuba diving and you go down underwater and you go 406 inches underwater, about 30 feet, 10 meters, what's the absolute pressure on you? About 30 feet underwater. 2. Very good. The normal atmosphere from the air and the pressure from the water, which when you're 30 feet down is equal to an atmosphere. So you have the water creating a pressure equal to the atmospheric pressure and the air creating atmospheric pressure. So your absolute pressure 30 feet underwater would be 2 atmospheres. The difference to us, because we're used to atmosphere, so we're already at 1. We go down, we just feel a difference of 1. But technically, there's 2 pushing on us. Boyles Law. I'll write it down. Let's show it to you first. Boyles Law basically relates pressure with volume. Most of you, your gut probably has this one right. That if you increase the pressure on something and it's free to change shape, like taking our balloon underwater, what happens to the pressure as you go down? It increases, and if the balloon can give, what happened to its volume? It decreased, it shrunk. That's essentially Boyle's law. If you change the pressure, then the volume changes. Let's do that with a balloon. This is in a bell jar full of my hot air. Here's a vacuum pump. So I'm going to be pulling the air out from around the balloon. There's still air inside the balloon, but I'm going to pull air out from outside the balloon. It's a big Easter egg. So the pressure difference changed. The pressure inside the balloon didn't change because it's fixed. It's contained. If you lower the pressure outside of the balloon, this greater pressure made it expand. Right? And if you let the air back in, there, now the pressure inside and outside the balloon is the same. And it doesn't get bigger or smaller. If I could increase the pressure out here, it would shrink. So let's write down Boyle's law. That's all there is to it. It's a guy's last name. He was a scientist. Figure this, or at least he gets the attribution. It's basically the pressure and volume at one point equal the pressure and volume at another point, or just think of it as that ratio is always constant. Now, if you guys remember your chemistry and ideal gas law, you've seen PV equals nRT. It's one way to do it. Pressure, volume, and temperature. These are constants based on what you're dealing with. Well, Boyle's law works if the temperature is staying constant like this. It's all room temperature. So basically, this is all constant. So it's nothing new than ideal gas law, if you're familiar with that. It's basically just saying this relationship stays constant. So in this case, you have pressure and volume. We have a pressure, we have a volume. On the other side, the volume got bigger, didn't it? It expanded. Because what happened to the pressure? Yeah, we decreased it outside of it. But the ratio stays the same. Or I would usually draw this more like a big P, little p, big V. Questions about that? Let's see, application. One I probably see a lot is your food. Oh no, that's the temperature's changing. Scratch that. I was thinking of food and Tupperware. Well, let's do another one because I like this one even better. You guys know what shaving cream is made out of? Yeah, I don't either. A bunch of stuff I can't pronounce. Palmacitic acid, tritylenistearic isopentane, yeah, whatever. But the number one ingredient is actually air. There's a lot of air trapped in there. It's like a whole bunch of little bubbles, a whole bunch of little balloons. And they're at a certain pressure. And it's equal to the pressure outside. Well, let's lessen the pressure outside, shall we? Just like the balloon, the pressure's greater inside the trapped air. And as we lower the pressure around it, it expands, the volume increases. Oh yeah. And I'll stop before it gets sucked into the pump. But now one thing that's different than the balloon is when you let the air back in and equalize the pressure, we're going to increase the pressure so the volume should go back down. And it does. But these cell walls, the bubble walls, collapse. And so it actually gets pretty flat. This doesn't collapse. But that's fun. It's a mess too. But you guys are worth it. I'll clean it up afterwards. All right, let's do another difference in pressure. This is one I wanted to do last time. Need a volunteer for it. Who would like to get vacuum packed? Feel this atmospheric pressure that we take for granted. We can only feel things when we have a difference. All right, Mark, you're up. Unless you want to get on your knees. Either way, I don't care. I'm just trying to make it more comfortable for folks. Well, if you're worried, let's just put you on your knees. So climb in there, get down on your knees, pull it up as high as it can go. I'm going to take this shop vac. All right, scoosh on down. Go ahead and rest at the bottom there. I'll get over here. You're on some. I've had bigger than you fit in this. So we're going to do it. We're going to make it happen. All right. Down, boy. You're a big person, aren't you? Yes. Well, it'll still work. You'll get the idea. Okay, you hold that in there. The reason you can relax a moment. The reason I put Nerf ball on there is if I don't, the air is going to push the bag into the hose and seal it off so it can't pull any more air. So it's porous. It lets the air through, but not the bag. All right. Let's try to seal this up as much as we can. If you guys ever find much bigger bags, let me know. This is the biggest I've found yet. All right, we'll give it a go. Get that part. All right, stand up. I'll fall over. Feels funny, doesn't it? Yeah. Yeah, you can still feel it. Thank you. Anybody else want to try it? It's fun. Max, you want to go for it? Really? Did it hurt?
No.
See, you're fine. I'm not going above your head. It's for science.
What happens if you put your head like in?
I've done that. Well, one, I have to hold my breath because you can't breathe.
Oh, yeah.
But the biggest thing, it hurt my ears because of the pressure difference. And the second time I tried it, it hurt my eyeballs. It would push on my eye. That wasn't fun. Yeah, go ahead. You want to try the bucket? All right, let's give it a go. Yeah, it doesn't matter. Go ahead and have a seat, and we'll try to pull it up as high as we can and give you an experience. Yeah, it's not a big bucket. You have to balance yourself. All right. All right, you hold that.
Hey, what do I get if I stand up?
Well, you can buy me a new bag because you'll break the bag. All right, hunch down as far as you can go. He's a little farther in. We'll give it a go. Here, just try this. Can you lift your arm and wave to the class? Good job. I like this demo. Thank you guys both for helping. I like this demonstration for two reasons. Physics-wise, I like it for a lot more just because it's fun. But the difference in pressure is actually not that great. Shop vacs and vacuum cleaners don't remove all the air. They maybe remove 10, maybe 20% of the air, which isn't a huge difference. But if out here in Salt Lake City, the atmospheric pressure is about 13 pounds per square inch, because we're higher up, inside the bag, we've maybe removed 2 or 3 psi. So that's the difference. Not huge. But remember that pressure is force over area. So the force that you feel in the bag is that difference in pressure. Whoa, hello, come back. That difference in pressure, that gauge pressure in between, times the area. Which area? Your area, acting over every square inch of your body. There's a difference of 3 pounds per square inch. And you have a lot of surface area. No offense. So it's enough force that, yeah, it's hard to stand up. It's hard to move your arms around. So we just vacuum packed it. You can crush things that way. Do it with a pop can. Empty pop can. Works like a charm. Okay. What if, they have these weather balloons, like this helium balloon. This floats because it's displacing air. What if we could let that go up into the atmosphere? What would happen? Let's think this through. What would happen? It's going to start going up, I'll give you that much. Then what? It blows up? Why? What about atmospheric pressure? It gets less when you go up. So that's just like these. If you lower the pressure around the helium, what will the balloon do? It expands. That's Boyle's Law. If the temperature stayed the same, that affects things a little bit. But so yeah, it's that difference in pressure. You lower the pressure outside, and the balloon will expand. Boyle's Law. So it gets bigger and bigger and bigger, and eventually can pop. They have these huge weather balloons. They can be like the size of this table sometimes by the time they get up there. But something else happens also. As the higher and higher up you go, the pressure decreases. What happens to the density of air? It was in your book that we discussed it last time, but do you guys remember? What do you think happens to it? It decreases. The higher up you go, there's less air until you get into space. So the density decreases also. Let's see, what was buoyant force? It's not depth dependent, it's volume dependent. dV. G. So the volume gets bigger because the pressure decreases, right? The balloon tries to expand. But the density decreases because there's less air up there. So that goes down. And at some point, they balance, and the balloon no longer goes any higher. So we watch it, and it goes up and up and up, and gets bigger and bigger, and goes up and up and bigger and bigger. But at some point, if it hasn't popped yet, it hovers and becomes neutrally buoyant because this balances its weight. Look at it this way. It's bigger, so there's more buoyant force. It goes up. But at some point, it can't displace, who cares how, it's displacing a lot of air, but that air is a lot less dense. It doesn't weigh as much for the same volume. So that makes the buoyant force go down. And at some point, it stabilizes. And it just hovers until something else happens. That's kind of cool. Any questions you can think of at the moment? Yeah.
Boyles Law explains why things are a little bit like more puffy than
Yes. Packaged goods, usually like groceries, yeah. They're like more turgid. The air inside's tighter. Yeah, that's this. Say you package your potato chips in California at sea level, atmospheric pressure. You close the bag up, and now you bring it to Salt Lake, which is higher up. The pressure's less, so what did the bag do? It's tighter. How many have had something explode in your luggage after an airplane flight? Because it might have been turgid already, and then you go up. They pressurize the cabin so that we stay roughly an atmosphere. Actually, it's not as close as you think, but it's bearable. They don't pressurize the luggage compartment, so the pressure really does drop. And yeah, your stuff in your luggage, especially like your toiletries. That's the word I'm thinking of. Yeah, they kind of, and if the container can't hold them, so I started putting all my toiletries in Ziploc bags before I go, just in case they explode and they don't ooze all over my clothes. But that's the same thing, and that is Boyle's Law. Very good. How about, oh yeah. Yes. The pressure underwater at 30 feet. I'll draw a picture. It helps me anyway. So if you're underwater, here, we'll just do a fish. Yay. If this is about 10.3 meters, that's because I remember what it is exactly. That's 405.5 inches of water. So what's the pressure here due to the water? Density, gravity, height, you do all that, it comes out to be 1 atmosphere. That's why. Does that part make sense? So just from the water on top of me, I'm feeling a pressure of 1 atmosphere. If you pull the fish up out here, he doesn't think he feels anything, but what really does he feel? 1 atmosphere. The pressure of the atmosphere is pushing on him. We're just so used to that, we don't think about it. We think it's 0 right here. So when we go down underwater, we feel a difference of 1 atmosphere from the water. That's the gauge pressure. The absolute pressure here is that water pressure and the air up here pushing, which makes 2 atmospheres. Because both fluids, the air and the water, are technically pushing on us. How many have ever had to plunger your toilet? Oh, less of you than I thought. Here's a rubber mat. It's not sticky. There's no adhesive. You just put it on the stool, and it'll hold it up. I have to balance its weight, but what's holding the two things together? The air in the room. Atmospheric pressure is pushing down on the top and on the bottom. What you don't realize is when I lift it up a little, whoosh, or when I put it on, some of the air in between gets pushed out. So there's less air in between. That lowers the pressure in between the two. So there's greater pressure out here from the atmosphere, and it sandwiches them together. And remember, that pressure, that little difference in pressure, 3 psi over here, I don't know what it is, probably even less over here, but that acts over every square inch on the top and the bottom, and that creates enough force to hold up this guy's weight. If you let the air back in, like this, whoops, I missed, then the pressures equalize, and it falls. That's how your plunger works. It's a suction cup. Here's 2 suction cups. You can push them together, center them, push them together. Some of the air gets squished out, and now the air in the room holds them together. Okay, Lanny, pull it apart. Come on. That proves my point. Yes, you can pull them apart, but it's hard. Okay, put you on the spot, Mark. You look stronger than I am. Here, stand up so they can see you.
Can I twist up?
Oh, yeah. Now, these have a release valve, so if you want to cheat, oops, push the air out. But if you just let the air back in, piece of cake. Historically, the mayor of Magdeburg, the city of Magdeburg, I think it was in Germany, Otto von Magdeburg, long story. he did a display for the town. Oh, it was for the mayor of that town, that's what it was. So they often call these Magdeburg hemispheres or plates or whatever. What he did is he took a sphere, big metal sphere, maybe this big, cut it in half, and made a gasket so that it could push together. And he got rid of some of the air from inside it with an old style vacuum pump, just a little air. So it stayed together like that. And then he got a team of horses on one side and another whole team of horses. I mean, we're talking like 8 horses over here, 8 horses over here. They couldn't pull it apart because of the difference in pressure acting over all those square inches, Pascal's principle, uniformly distributed over every square inch. A lot of force, more force. The atmosphere could exert more force on both sides than the horses could. And they couldn't pull it apart. Well, the mayor was impressed, and vacuum pumps started getting better after that. They started making these things called a lily pad. You want to keep your salad fresh? You just pop it on. No need for saran wrap anymore. And let the atmosphere hold them together. It's sealed. And I like this one too. Here's a bottle with a hole all the way through it. I'm going to put this balloon inside. Sorry. This is fun. You can do this with a water bottle. You just poke a hole in the bottom. So it's open. It's not inflated because the air here is the same as the air around it. So I have to increase the pressure here to blow it up. But what if you seal it, that hole? Can you blow it up? Why? Because as I try to, as I try to make it bigger, it compresses the air inside and increases the pressure. There's greater pressure inside than outside, and I can't. It fights. So what happens with like this is it pushes the air out. I pushed the air out, it could inflate. But now I sealed it. You probably couldn't tell. The balloon collapsed just a little. That lowered the pressure inside the bottle, around the balloon. And now the pressure out here is larger than the pressure inside the bottle. Okay, so you can write this back to the lung with Rich. And so the air in the room is holding the balloon open. If I equalize the pressure, it deflates. Okay. The last part of chapter 14, we start moving fluids. And I have time to show a few demonstrations. Probably do a little more on Friday. Basically, if you start moving a fluid, the motion of it moving can also change the pressure. That's Bernoulli's principle. Bernoulli. Where the speed, this is in your book, of a fluid, so it can be a liquid or a gas, increases. So if there's a change in the speed, if it's going fast somewhere, the internal pressure, so not the pressure around the fluid, but inside the fluid, changes. And if we're increasing the speed, then that internal pressure decreases. So basically, don't think of it as cause and effect. Two things happen. If the fluid's moving faster somewhere, there's a corresponding drop in pressure inside that fluid. Or vice versa. If you decrease the pressure inside that fluid, it's going to speed up. It's going to go faster. That's Bernoulli's principle. Fluids in motion exert less pressure. From within the fluid, they exert less pressure the faster that fluid's moving. This is how airplanes fly. You can describe the flight of airplanes by Newton's laws completely, but you can also describe it by this because of this thing called lift. I'm going to start, though, with this demonstration. And you need one more equation to help us understand it. The equation of continuity. Basically, it says the flow of a fluid, the rate has to stay the same. This should make sense to you, too. You got your water flowing through your garden hose. What if you restrict the garden hose and you make it smaller? Does that keep water from getting through? No. How about the end of it? You know, you take the end and you put your thumb over it a little bit. What happens to the water? It shoots harder. See, as you change the area, it starts going faster. To keep the flow rate the same. In other words, the water's coming from the spigot, and it's coming out at the same rate, no matter what you do to the hose, as long as you don't close it off. So the flow doesn't change. The flow rate, sorry. So if you make it go into a big pipe, it doesn't have to move as fast to get the same amount of water through. But if you make the pipe narrow, now it has to go faster to keep up with that same flow rate. That's the equation of continuity. I sum it up like this. The air area of one spot has to equal the area of another spot, or again, you can think of that as constant. So let me draw a picture. Here's a pipe. Here the area is big. Let's say A1. Here the area, cross-sectional area, is smaller. So you got these, we like to picture streamlines. This fluid's flowing along, going like this. This could be air or water. And it gets here, and it sees a constriction. they're going to get through, you know this, but they get closer together and they get constricted. They're still moving that way. And the flow rate stays the same, so it has to speed up because you're fitting less through there. And so the velocity here is slower than the velocity here. Does that make sense? That's the continuity equation, because fluids can flow. And when they're moving, this happens. So in my mind, anytime the fluid speeds up, there's a drop in pressure, or vice versa. And this can kind of help us understand when and where it would speed up. If it gets constricted, it speeds up. So what do you know from Bernoulli's principle? How will the pressures in the internal fluid compare? That's right. There's more pressure here than there, because this is Bernoulli's principle. If it's going faster, there's a decrease in the internal pressure. And that's the pressure this is exerting outward. That's what this demo can help show. I have a shot back behind the wall, and this time I'm going to blow air instead of pull air out. It's going to blow through this tube. See, it constricts, and then opens back up. And this is open to atmosphere. And this is just colored water. So atmosphere comes along, pushes on this one, this one, this one, and this one. That's why they're at the same height, because it's the same pressure. This column of water is adding pressure here, but it's the same pressure. The pressure this column of water exerts is enough pressure to hold up this column of water. But now we're going to move the fluid. Let's predict what will happen, and then we'll do it and end. I'm going to start moving the fluid. It's going to go from this area and then get smaller. So what happens to the velocity of the air here? It goes faster. That's continuity equation. Bernoulli's principle then says what happens to the pressure at this point? See, where the speed of a fluid increases, the internal pressure of that fluid decreases. So the pressure in the air is going to decrease the faster it's moving here. So there's going to be a drop in pressure here. If the pressure drops here, but not in the room, what do you think will happen to this guy? Will it go up or down? What's pushing it up? The greater atmospheric pressure? Because it dropped on top of it. This will put. Let's try it. It does. This air, you can see the corresponding increase, the greater pressure here, because this one actually goes down. And it makes that difference easy. You can also think of it, the air kind of gets constricted and it kind of backs up, and that increases the pressure here. But it's also because it's moving. So do it again. Move the air. It goes faster here, so there's a drop in pressure, not pushing down on it as much. And the atmosphere can make it go higher. That's Bernoulli's principle. We'll apply it to a few things at the beginning of Friday. And Friday we start chapter 22 on electrostatics. But come with questions on this fluid stuff, and we'll ask them. See you later.